Welcome, everyone. I'm Zhaojun Yin from Bioanalytical Sciences in Genetics. Today, I will present flow-based cellular kinetic and phenotyping assay development and validation for TCR-T cell therapy program. Probably many of you have learned about this type of assays for CAR-T program from either webinar, conference, or publications. In my talk today, I will highlight some considerations in assay development and validation for TCR-T programs. This is the outline of my talk today. First, I will give a brief introduction about genetically engineered T cells, including CAR-T and TCR-T. And I also provide some background why cell persistency and memory phenotypes are important for cell therapy. Then I will discuss some key considerations in assay development and validation process, such as TCR staining and assay precision assessment. One of the most promising cancer immunotherapy area is adoptive cell therapy, where patients' own T cells, either tumor-infiltrating lymphocytes or genetically modified T cells, are infused back to patient's body to attack tumor cells. In this talk, we will focus on the engineered T cells, where the T cells are extracted from patient's blood and genetically modified to encode receptors that recognize tumor-specific antigens. In general, there are two types of genetically engineered tumor-specific T cells, including T cell receptor or TCR T cells, and chimeric antigen receptor or CAR T cells. This slide shows the structure details for two types of engineered T cells. As you can see the graph on the left side, CAR-T has a chimeric receptor formed by combining a single-chain variable antibody domain with signaling components from immunoreceptors and co-stimulatory molecules. The CAR directly recognizes tumor surface antigens and are not restricted by MHC molecules, while the TCR-T has a modified T cell receptor, which can recognize peptide MHC complex present by tumor cells. The peptide can be processed from intracellular or surface targets. Another big difference is that TCR receptor complex has 10 subunits, and CAR only has one subunit. So there are much more co-receptors in TCR T cells, and the cells are usually less antigen dependent. One of the biggest difference between T cell therapy and antibody drug is that the T cells can expand, differentiate, and last for a very long period of time. It has been demonstrated that the persistency of T cells is very important for clinical response. Here is one example published in 2015, where the NY-ESO1 specific TCR T cells were used for melanoma treatment. The data table here summarizes the relapse time, persistency, and antigen status for patients who had progression after treatment. By comparing with persistent data without relapse, the author concluded that no antigen-positive tumor relapse is found if the persistency of TCR T cells is at least 6 cells per microliter of blood. Several factors could contribute to the T cell expansion and the persistency in vivo, including cell dose, tumor burden, conditioning regimen used for lymphodepletion, and cell product characteristics It has been well studied that the T cell persistency correlates with the memory phenotype of T cell product. The cartoon on the left shows the proliferation capacity and effector function of different T cell phenotypes. You can see both stem memory T cells and central memory T cells can self-renew and therefore have very high proliferation capacity and will be more persistent in vivo. A study with GD2 CAR-T published in 2011 shows that every unit increase in the percentage of central memory T cells in the product was associated with 6.6 unit increase of log duration of CAR-T cells. The phenotypes of T cells is dynamic, and it changes over time after T cell expansion in vivo. Here is one example published in 2019 about WT1 specific T cells used for leukemia treatment. As you can see from the graphic on the right side, the product is mainly effector memory T cells. And over time, it slowly differentiates into central memory and effector T cells. Similar observations also reported for melanoma-specific CTLs. Now we can see the purpose of cellular kinetic and phenotyping assays are really to confirm the transgenic TCR is expressed on the cell surface, which cannot be verified by PCR assays, to measure expansion and persistency of TCR T cells in terms of frequency. For example, the percentage of parent CD3 T cells, the absolute cell count per microliter blood. The absolute cell counting is important because the frequency is a relative measurement. Sometimes frequency can be similar, but the absolute number of cells differ a lot. To monitor the phenotypes of T cells after expansion in vivo, including stem, effector, central memory T cells, and effector T cells. This is an overview of cellular kinetic and phenotyping assay process. We start with whole blood sample, and then stain cells with MHC multimers and antibody cocktail. This is an example of panel design. Our product only has CD8 T cells, so we have CD3, CD8, CD45, and MHC multimers to identify the T cell product. A dump channel is also included to exclude B cells, monocytes, and NK cells. We also have two differentiation markers for phenotyping. I want to mention that the phenotyping markers are not unique. There are also other markers working fine, such as CD95, CD27, and CD62L. After staining and red blood cell slices, the sample were run with BD-CAN2, and the data analysis is performed with FlowJo. We use BD CD45 true count to help determine the absolute count of T cells in the blood. The tubes contain lyophilized fluorescent beads. After adding blood and CD45 reagents, the absolute number of lymphocytes in the sample can be determined by comparing lymphocyte events to bead events. Then the number of T cells can be obtained by conversion from the frequency in lymphocytes. In this slide, I'm going to talk about the TCR staining, which is unique to TCR T cells and also the most important step in the assay development. Traditionally, MHC tetramers were used TCR staining. In recent years, the dextramer become more and more popular, especially for the low affinity CD8 T cells or CD4 T cells. The dextramer is based on dextrin backbone and has been shown superior identification of antigen-specific T cells due to higher avidity. You can see from this example, the detramer staining has much better separation compared with tetramer staining. Overall, the dextramer with bright dyes, such as PE and APC, are preferred to achieve the best sensitivity. However, in some cases, we have seen dextramer have non-specific binding to CD8 T cells for certain peptide MHC complex. Here is one example from literature. The first graph showed dextramer staining with irrelevant peptide, which is more like S-type control in the T cell staining. The second graph showed the dextramer staining with cognate peptide. We can see about 5,500 T cells are detected. However, we also noticed that the TCR negative CD8 T cells also shift in the dextramer PE channel, suggesting the non-specific binding of dextramer with CD8 T cells. With non-CD8 cells doesn't show this type of non-specific binding. So this non-specific binding actually makes the MFO control or S-type control not appropriate for the gating. This issue sometimes can be addressed by optimizing the staining protocol or using the autogating approach. Overall, the dextramers still perform much better than tetramers. As you can see the graph on the right side, the tetramer staining only detects 361 T cells, which is only about 7% of T cells detected by the dextramer. Another consideration of TCR staining is the impact of anti-CD8 antibody. We know that CD8 is a co-receptor to stabilize peptide MHC1 TCR interactions. The average affinity between CD8 and peptide MHC1 is estimated about 145 micromolar. Anti-CD8 antibody might reduce or enhance the TCR staining depending on the clones and the staining protocol. Here is an interesting example from the literature. When anti-CD8 clone OKT8 add to T cells and then do the tetramer staining, a much stronger signal was obtained. However, if another clone DK25 was added, the tetramer staining was dramatically decreased. I would like to mention that in normal practice, we always add tetramer or dextramer staining first, then antibody cocktail next, including the CD8 antibody. But it's still worth trying a couple of different anti-CD8 clones and see how the staining pattern looks like. Next, I'm going to go through the validation of cellular kinetic assay. Actually, there's no official guidance document for validation of flow cytometry assays from health authorities. Recently, CLSI released its 62 guidance last year that can be used as a good reference. In addition, the journal Bioanalysis also publishes white papers each year after WRIB conferences. In our cases, the validation parameter will be fit for purpose based on industry best practice with emphasis on sensitivity, precision, and stability. We typically assess specificity in method development stage by looking at dextramer staining with irrelevant peptide, MFO control from at least 2 healthy donors, but with TCR T cells with different knocking efficiency. The goal here is really to verify the staining patterns and the gating strategy. For sensitivity, we basically follow the recommendations from H62 guidance. The LOB and LOD are evaluated using unspec samples with minimum 10 data points from a minimum 3 donors and at least 2 analytical runs. The LLQ is evaluated using spec samples. Here you can see we have 3 validation criteria for LLQ. The signal must be larger than LOD. The CV across 3 replicates must be equal or less than 30%. The gated events should be equal or larger than the minimum number of required events, or MRE. I will discuss about MRE in a moment in the following slides. The precision assessment, including repeatability and reproducibility with different analysts, days, and instruments. The repeatability is evaluated with 4 specking samples and 2 QCs. The reproducibility is evaluated with 2 QCs. The QC here are prepared by spiking frozen TCR T cells into the commercial available fixed blood Cytocheck Plus. Sample stability is very important for flow cytometry assays, especially when whole blood is used. We normally start to evaluate sample stability in method development stage, but look at types of anticoagulants, types of collection tubes, and storage temperature by checking the frequency of cells and memory markers. The stability validation is performed by using spec samples and test up to 4 days. We also evaluate stability of dexamer, one of the most critical reagents in this assay, by using similar approach at sample stability. Here is one example of a nested design for precision assessment, where 4 spiking samples and 2 levels of QC are tested on different days by a combination of different analysts and instruments. Each sample is run in triplicate, and the precision can be analyzed using various components analysis. We mentioned the minimum number of required events in the LLOQ assessment. The number of events collected in flow for a period of time generally follow Poisson distribution. Based on the basic statistics, we can get this formula. The percent CV of gated events is equal to 100 divided by the square root of the number of events. For example, if we have 25 events in the gate, the percent CV will be expected around 20%. That means if we target CV 20%, we should collect a minimum of 25 cells in the gate. I would say this number should be the starting point. In reality, we always see variability from analyst, instrument, or even number of gated events in the blood samples due to cross-reactivity or non-specific binding. So evaluating MRE during precision assessment is a more appropriate approach. Actually, the MRE can be achieved by using more sample volume if feasible. In other words, we can do some number crunching to decide what's the minimum sample volume we should start with in assay development. For example, let's assume 25 TCR T cells are required in the gate, and by average, there are about 30% lymphocytes in the blood mononuclear cells. And there are 60% of CD3 T cells in lymphocytes. And our target LLOQ for frequency is 0.1%. If we want to start with 100 microliter sample volume, the minimum amount of mononuclear cells in the blood should be around 1400 cells per microliter. If the cells number is below this, we should increase the sample volume accordingly. Here is a quick summary of my talk today. Flow cytometry-based cellular kinetic and phenotyping assays inform the persistency and functionality of TCR T cells, which has been shown to correlate with durability of clinical responses. The TCR staining step is unique for TCR T cell assays and also very crucial to achieve optimal assay sensitivity. Reagent design and protocol optimization are key factors for success. Sensitivity, precision, and stability are key parameters evaluated during validation. Additional assessments such as reagent titration, incubation time and temperature, red blood cell lysis, and processed sample stability should be optimized during assay development. Before I end up my talk, I would thank my colleagues from bioanalytical sciences and biomarker development in genetics who work on this program, especially the support from Kip and Patty on the T-cell programs. I also want to thank your attention, and I'm looking forward to discussing with you in the end of the webinar.
Yeah, hello from my side. My name is Masilius Moos, and I'm with Miltenyi Biotech, and today I would like to present what we can contribute on the standardization of flow cytometric assays. I would like to start with a short agenda. So first, I would like to show where actually flow cytometry resides during cell manufacturing. Then, of course, the relevance of standardization. What are different sources of variation? What is our contribution to reduce these variations? And then, of course, with a short summary in the end. So here you can see a classic example of CAR T-cell manufacturing from a patient sample to the actual patient treatment. And you can see that throughout the process, here done on the Clinimax Prodigy, this is accompanied by flow cytometric analysis throughout the process. It can start with patient eligibility screening, but of course then during manufacturing we have constant in-process control and quality control steps, and then of course in the end the QC release testing, and after the patients received the CAR T cells, of course also potential CAR T cell monitoring. Why is standardization such an importance? And I would like to show this publication here from 2015, which actually found that about 50% of annual research money is actually wasted on irreproducible preclinical research. And that, of course, results in tremendous economic damages and obviously also to a longer drug development and in some to higher costs for development of therapeutics. So what are different sources of variation? Of course, that is, I think, a given is the donor variability, but that is, of course, something which often cannot really be controlled. That is intrinsic to, let's say, a patient sample. However, there are many other things where things can be optimized and controlled to reduce variation. And that is, of course, reagents. So you would like to reduce lot-to-lot differences and have a high specificity. Of course, with the instrumentation, you can make sure that you have a low variability. Then with the actual data analysis and the reporting by trying to take out the human factor as much as possible. And in the end, of course, overarching by having the best protocols you can have. So what is our concept here for flow cytometry standardization? Coming in, as I outlined before, with the reagents. So we would bring into the field the reaffinity recombinant antibodies. And we think they are great because they are derived from a defined DNA sequence and then, of course, recombinantly expressed. They are produced under highly standardized conditions, which, of course, yields a high lot-to-lot consistency. There's only one isotype control needed because they are all based on the same IgG1 isotype. And I think also very important is that no FC blocking is necessary because they all feature a mutated FC reagent, which leads to far less background signal. Here is an example, and you can see here that is a side-by-side staining of cells, and you have here a staining with a hybridoma clone, and you can see here this unwanted background in here, which actually comes from the granulocytes. And by using here, it's the REA613, it's a recombinant clone, also staining CD3, you can see that you get a much better separation and overall, of course, a much cleaner picture. And that is why we recommend these reaffinity antibodies, because you can do the staining in the absence of any FCR blocking reagents and get better results in the end. Also new is our StainExpress dry antibody cocktails. So they are pre-formulated dry antibody cocktails. They can easily be combined with any of our CAR detection reagents. And of course, as already mentioned before, they are again also based on our reaffinity technologies, which means they feature recombinantly produced antibodies. And that, of course, leads to less handling steps and obviously, since everything is pre-formulated, in far less variation during assay setup. Switching over to the instrumentation. So here you can see that is our MaxQuant 16 flow analyzer. To reduce variations, we do provide IQ/OQ services for instrument qualification, and this also includes official documentation to maintain GMP standards. Then along comes with these machines the Smart Gain technology, which means that you can transition instrument settings from one machine, which would be the master machine, and from there you can transfer the settings to other machines and you will get similar results. And here's one example where you can see here the setting on the master machine and then transfer of the settings to the other machines, and in the end you get very comparable data. After the acquisition of the data, of course, analysis and reporting has to be done. And of course, here a sample-to-sample variation obviously always leads to the necessity of adjusting the gating. And here's just an example of two donors, which gave different results, which of course cannot be gated the same way. So when done manually, this is obviously or can be a source of variation. And we would like to bring in the express modes, which are add-on tools for the MaxQuantify software running on our flow cytometers. And they bring, on the one hand, a predefined setting, but also an algorithm-based analysis, which allows for faster and reproducible sample analysis. Along as also with the CAR detection reagents, these expression packages are also tailored for CAR T-cell analysis. And as you can see here, this is the example from before, but now analyzed with these express modes, where you can see with an automatic gating adjustment, a correct gating of those two samples. That is, of course, very time-saving, because using these automatic gating algorithms is much faster than if you would have to do the analysis by hand. But of course, you also gain a high reproducibility, because the algorithm is, of course, obviously always doing it the same in contrast to a manual user. Again, also for the Max Quantify software, there is available a 21 CFR Part 11 module, which enables compliance for electronic records and signatures, and of course then also eases the submission of documents to the authorities. It comes with an audit trail. It comes as a closed system with electronic signatures. It has an advanced user and also a role management system, and of course also a electronic batch record. With that, I'm already coming to our protocols, because no process is as good as the corresponding protocols you are using to run your procedures. And with that, we can and we would like to help by offering specific clinical cell manufacturing training courses and also CAR T-cell analysis user trainings. So these are the sources of variation that can be addressed. In the beginning, I mentioned also the donor variation. That is, of course, not such an easy one. But reagents we can address with our reaffinity antibodies. On our instruments, we have the SmartGain technology and IQ/OQ services. For the analysis, we provide the express modes, which provide an algorithm-based automatic data analysis and supporting you with your process development by our user trainings. And here I'm already at the end, and I would like to thank you for your attention.